Okay, so Siva is going to give the next talk, who's going to be about A star for bounding shortest paths in the graph of convex set.
Thank you. This is joint work with Kaarthik at Los Alamos. So before I get into the method and other things, let me define what the problem is. So we all know what the shortest path problem is. You're given a graph, and each edge in the graph has a cost, and you want to figure out what the shortest path is from the source to the destination. Now, in the graph of convex sets problem, each node is associated with the convex set. So for example, you have something like this, and it's just called the graph of convex sets. And the problem here, the shortest path problem in the graph of convex sets, is to basically find a sequence of sets to visit and choose a point in each of the sets you're visiting, right? So if I give you the path, then choosing the points is a standard convex program. It's very easy to solve. It's a continuous optimization problem. If you select a point from each of the sets, then it reduces to a shortest path problem with discrete variables. So that's also relatively at least well understood. But here is a problem where you have both discrete and continuous variables. So that's the challenge here. Now, so this problem was actually first formulated in 2022, I think 2022, 2023, and by this robotics group here. So the general version of this problem is known to be NP-hard because the cost of traveling between any 2 points in the corresponding convex sets can be any metric. It could be L1, L2. You know, there are generic metrics you can use for that. So the general version is NP-hard. I was interested in the problem where you have the cost of traveling is just Euclidean distances, right? So now just let me tell you why we were interested in this problem. There were two reasons why we were interested in the problem, because this problem is a part of the standard, very classic shortest path problems in 3 dimensions in the presence of static obstacles. It's known to be NP-hard. And there are lots of approximation schemes for this problem. But numerically, at least when you try to implement them, it's pretty inefficient to get good bounds in a relatively short amount of time. So there are theoretical results, but it's hard to implement and get good bounds in the time that we wanted. And so this is first motivation. The second one is, by the way, just to let you know, so if you're given a problem like this in 3D, one thing you can do is to take the free space in your domain, and then you decompose it into convex sets, and then you apply this shortest path algorithm for the graph of convex sets. So that's the relationship between my problem and this problem. And there is also this other motivation. So we have been working, myself and my colleagues at CMU and China have been working on this multi-agent pathfinding problem in many domains, and particularly we are interested in problems in continuous space and time. And it's a very hard problem if you want to really find the optimal solution. And one of the sub problems we had to do for this one is that of figuring out what your shortest or the least cost trajectory is in the presence of moving obstacles. And so our problem was like a special case of this problem. So that's also another reason why we were interested in this problem, right? Now, let me explain what, how we go about doing this, right? So this problem can be formulated as a nonlinear program with essentially bilinear constraints. So for example, suppose let us say that you take any 2 sets. So here I call them as sets, but they are also nodes in the graph. And let's say these nodes are u and v, and suppose let's say xu and xv are the corresponding points you choose from the sets. Now the objective, the cost of traveling is basically cost of the points that is the cost of traveling between xu and xv and your yuv variable, which tells you whether you're actually traveling from the set u to set v, right? So you have a combination of both continuous and discrete variables, and if you choose the Euclidean traveling cost, this is what your objective function turns out to be, right? So it's a product of continuous and discrete variables. Now the main idea that the folks in this paper did was to basically lift the problem space into a higher dimensional space. So they take the product of 2 variables, xu times yuv, and they assign a new variable, and then the other variable xv times yuv to another variable, and then they introduce these new variables and reformulate the problem in terms of these new variables and the discrete choice of variables that you have, discrete paths that you have. And this essentially what happens is that even though you lift the problem to a higher dimensional space, you get a mixed integer convex program. So it's not a nonlinear program anymore. It's a mixed integer convex program. And the really nice thing about this formulation is that it happens to give tight relaxations. So at least for the examples that they were looking at, small scale, moderate scale problems, it gave really tight relaxations and good bonds. And this is what we were also after, and that's the reason why we were interested in this. Now, what we wanted to do was to somehow take this method here and try to make it faster for relatively larger size problems. So that is where we came in. So we thought, so if you want to make it faster, so you could inject this heuristic information into the solution process. So just like how we have A star, the question is how do we integrate this heuristic search into this convex program solution procedure, and how do you get good bounds? So that's the question we were interested in. And the problem here is that unlike the standard shortest path problem, the future cost of traveling from a node also depends on how you entered that node, right? So your future cost depends on the history, and so greedy addition of nodes while fixing the path that you came to that node doesn't help you. It doesn't lead to an optimal solution, right? Okay, so our algorithm, so again, we assume that each set or each node has a heuristic cost to the destination, and the paper talks about how you generate these heuristics. So I'll just skip that for the moment. So this is what we do. Our algorithm basically tries to mimic A star. So what we do is in each iteration, we pick the next best node or set to visit and a path to travel from the origin to a point in the set corresponding to the new node u that we are picking. So for example, just for notation, suppose let's say that this is a closed set that you have at any point in the iteration. So these are the nodes you've already explored, and these are the new nodes that you're trying to choose from, right? So in this iteration, we solve this optimization problem where we pick the set in this open list, as well as the path from the origin to that set that minimizes your total cost, right? So once we pick that node, we just do the standard update like what we do in A star. So we update your closed set and the open set, and then we again redo this problem, and then we just keep on marching forward, and we do this until the bounds cannot improve, right? So this is our algorithm. Now the key thing here is in figuring out what your path is and the next node to choose is, because that's where all the optimization happens. Everything else is pretty much the same as how it occurs in A star. Now, to do that, we formulate first we formulate a nonlinear program in the same style as what the other paper that did this problem. So here what we have is we have this g cost of actually coming to this node, travel cost, and we also have this new heuristic cost that is dictated by the by your lower bounds that you already have. And then this is of course nonlinear, right? So we convexify them. So we follow the same procedure as what is there in the earlier paper. So we introduce these new variables, lift the problem, we convexify it and all that. So this is how we get we solve the relaxation as well as the integer program in each of the iterations. So once you do that, so these are I'll just go through the main features of the algorithm. So the set that you pick, the closed set that I was talking about that you pick, need not start from the origin just like how we do in A star. You can pick the set anything you want as long as the origin belongs to that set and the destination does not belong to that set. So that's the only constraint that you have. And the second point I want to mention is that these sets, so we did quite a number of experiments, and we realized that the initial choice of sets can make a big difference in making this algorithm run faster. And we found out that this initial set, closed set S, informed by a star based heuristic, leads to the generation of the bounds quickly, relatively fast. And in fact, the heuristic that we use is really simple. What we do is, it's a two-step heuristic. We just, from each set, we sample a point. Typically, it's a centroid of that set. We run your A star algorithm. You get your set of closed nodes. and then those nodes is a starting point for our algorithm, right? So that's the way it works. So this is the approach, and we show in the paper that pretty much, I mean, at least in, numerically, the bounds that are generated by our algorithm is pretty much the same as the bounds generated by running the convex program on the entire graph. And we work with fewer nodes because the initial set yes that we pick is informed by this A star based heuristic. So the better the heuristics are, the smaller the sets, and that's the reason why we solve smaller convex programs. And there are some other results. Of course, if the if each set in your graph is a singleton, then it just our algorithm just reduces to the standard A star algorithm. So anyway, I'll just show you some results here. So I'll just show you some simple few results at least. So let's just take the 2D case here. It's a maze here, so you want to go from this origin to the destination. We first construct the graph of convex sets, and in this graph we basically have 414 convex sets. So so let's see what happens. Now we actually have two heuristics that we have in the paper. The first heuristic is a simple Euclidean heuristic, so it's consistent but gives you poor bounds. It's very easy to compute. The second heuristic is an admissible heuristic, but it gives you really tight bounds. And so by varying the weights, we can go from we can change the strength of the heuristics, right? So if you take the weight to be 0, if it's just purely just the Euclidean based heuristic, this is what you see here. So the blue nodes that you see are the nodes generated by the A star heuristic. So this is the set of these are all the nodes that our A star GCS is going to work with. So this is the size of the convex program that I'm going to work with. In fact, if you just use the simplest heuristic, your size of the convex program reduces to just 288, right? From 414, you reduce to 288 nodes. And this path, the red path, is a feasible solution. And the stronger the heuristic values are, the smaller the sets become. So for example, this is 0.5 becomes 266, and then for heuristic for the weight 1, you're working with a convex program that has only 196 nodes. Now all of these things, so if you run A star GCS on all of these graphs, pretty much they produce the same bounds. It's just that your solution time gets faster and faster, right? That's the point here. And we also did 3D instances because that was our goal anyway. So we were not 2D instances. You can have other methods to do it, but 3D is the one where it's difficult to get bounds. So we have two maps here. In each map, we have 100 instances, and you can see these are relatively large maps, at least for this problem. And we generate our GCS. It's very hard to show you this thing. We tried our best to come up with a visualization, but this is what we have. So the main results are this, that our algorithm basically explored only 20% of the vertices in the graph. So instead of solving the whole problem on the entire graph, you only work with 20% of the vertices in the graph. And for 63% of the instances, our algorithm basically produced around 65% reduction in computation time. And for the remaining instances, so our algorithm is an iterative algorithm, but if you just stop the algorithm after the first iteration, you basically produce good enough bounds, right? That's what we observed. And so these are the main results. There are more results, numerical results in the paper you can refer to. Now, of course, the story doesn't end here. We thought it could really, this idea would really work for large graphs and all that. It's still, there are some issues. There are two main issues that are pending. One is relatively, I feel, easy to solve. The other one it's still ongoing work. So this whole approach relies on the fact that you have to decompose free space into convex sets. That might be a hard problem, but you can do that. There are heuristics to do it, and there are many ways of decomposing that. That's really not an issue. But the other issue is for multi-agent planning, we were really interested in we want to find tight bounds, but we want to do it even much quicker than what this method currently offers. So that second question is still harder, so it's something that we're working on. But yeah, that's my presentation. Thank you.
Thank you. Do you have questions? Just one here.
Thank you. Could we look back to where we have the convexified nonlinear program?
Yeah.
The next one, exactly.
Yeah.
No? So here you're doing this transformation that I know with the name of McCormick's transformation.
First order, yeah.
Exactly, you're converting a convex hull, no? So that constraint there, that there is the auxiliary variables. What is the arithmetic operation happening in the sum? It's the parentheses, no?
You're this one here?
Yeah. No, what's the notation for?
Oh, yeah. It's just a compact way of writing. So you have the flow constraints.
Okay.
So that's all. It's just flow constraints.
Okay.
There's nothing. It's a very simple.
I was like,
it's just compact to write. I just copied it from the paper.
No, fair enough. There was just some symbols missing.
Yeah, it's nothing.
Okay.
It's just first order approximation.
So
the nice thing here is that, of course, we all know about all these relaxations.
Yeah.
It so turns out that this first order approximation works really well for this problem.
No.
That's the thing that I didn't know about it. So that is the main contribution of the previous paper. What we did was to make it faster using A stars.
No, I really like your paper very much, actually. And my observation is that this is still a quadratic program linear with linear constraints, no, which is not easy.
Yeah, no. So this is a convex program with binary constraints. So if you look at the objective there, so the previous one was a quadratic program. You're right.
Yep.
But when you substitute the variables, the objective becomes like that's a Euclidean L2 norm.
Yep.
So it'll be basically just difference in variables. So it's still okay, but it's a binary convex program. It's still not trivial.
Okay.
But you can still do it. But the main thing is that the relaxations are very tight.
Exactly.
That's the main catch here.
That's good.
Yeah.
Well, I mean, and you consider less variables than the approach of Parillo and Rustedrick. Very, very cool work. Thank you very much for the presentation.
Thank you.
And coming all the way that I know it wasn't very easy.
Yeah, first time here, but thank you.
Okay, we have another question here.
Yeah, this question's gonna be, so there was another algorithm which is also using A star to explore graphic convex sets. And so the question would be are you familiar with it or not?
Yeah,
and if
of course.
So, it's not, they did it before. That's not my point. But, and if so, do you know what's the relationship? So,
Yeah.
So this was by Enrique Fernandez around 2018, right? So he was also using A star, right? And his heuristic was solving a semi-definite program in that case.
Oh, that work I'm not aware of.
Or no, it was solving a second order cone program in that case.
Oh, I see. I'd be happy to read that work.
I'm not
sure.
Probably the things that are different about it is, so in this case, you're trying to find you're trying to find a sequence of convex regions.
Exactly.
Right, which would have the minimum cost path.
Yeah.
It's a dynamical system where you assume that the dynamics is linear or piecewise linear. I'd have to qualify what it meant by piecewise linear. And then that the objective function could be quadratic. It could be like battery consumption.
I see.
Right? That the paths were of multiple vehicles, and you could have a norm constraint, which would say that they have to stay far enough away or together.
Yeah.
Right? So not the same problem, but it's interesting that it still has a lot of the structure.
I'd be happy to look at it. The only other work that at the same time that we were doing, the group from MIT who originally did this work also had an A-star algorithm, but their objective, they were working with upper bounds, whereas my algorithm works with lower bounds. So that's the difference between my work and that work. But I'm not aware of what the paper that you're saying. I'll be happy to take a look at it.
Right. Yeah, and we're next door neighbors too.
Oh, okay.
So that's why.
Okay. Thank you.
Cool. Thanks.
Thank you.
Other questions? We still have a little bit of time. There we go.
You were alluding to this, so I just wanted to ask to clarify. Your heuristic, the Euclidean, is consistent, but the other heuristic you have is not.
It's not. It's admissible.
So are you doing re-expansions in your A star?
We don't have to do it here. Okay. For the A star heuristic, yes, we have to do it. For the heuristic, for generating the initial feasible solution, we have to do that, going back and forth. But for my program, the convex, once you do that, once you get the set, I keep only expanding it. So I don't have to worry about, because the convex because I'm just, that's the whole thing here, right? So I'm actually solving the program to get the path. But for the first step, yes, you have to do the standard A-star thing. You have to go back and sets, nodes can be opened and closed, and again, you have to go back and forth.
But that's only your first initial step where you're
Yes,
establishing
exactly.
things.
That's right.
Okay.
That's right.
Thank you.
One final quick question? No? So let's thank the speaker again.
Thank you.